Today we're going to take a look at sliding friction, including both static friction and kinetic, or also called dynamic friction.
Three types of friction that we'll generally consider in this course. The first is rolling friction, which is usually fairly insignificant unless you've got a flat tire or something like that. So if we roll a marble or roll a bowling ball, they usually don't slow down very much. Rolling friction a little bit different than the others because if that friction's not there, the object can't roll. You need friction in order to have that traction so an object rolls and doesn't just slip. The second is fluid friction. Usually that means air friction for us. And what's significant about air friction or fluid friction is that friction will vary as the speed. So when you stick your hand out of a car door and the car is moving really fast, you experience a lot of air resistance because your hand is moving quickly through the air. And then the topic of this video is sliding friction. So that occurs when we have surfaces rubbing against each other and an object moving across that surface. So what is the cause of sliding friction? Well, if we magnify the area between the two surfaces, there would be microscopic bumps along those surfaces. And of course those microscopic bumps would kind of settle into one another, and that would produce friction. So the cause is microscopic bumps. And this leads to there being two different types of sliding friction. One to get the object moving, which we call the static friction. And that's because the bumps will kind of settle into one another. And the other type of sliding friction is while the object's moving, which we usually call the kinetic friction. And we can think of this as being when the bumps glide across each other. But they don't settle into one another. Now our little model with the microscopic bumps, it's simple and it works for us. It's good enough for us. There are more advanced models of sliding friction. Of course, the molecules contain protons and electrons, and that means there's going to be electrostatic repulsion and attraction, and that's going to have an effect as well. Now, the first question you should be asking yourself is, what does this force of sliding friction depend on? And let's make a couple likely guesses for that. How about speed? The faster you pull the block, will that make more friction? Turns out sliding friction isn't like fluid friction, and speed doesn't have an effect, at least to a first order approximation. Speed does not have an effect. Second guess you might make would be the contact surface area. So if I've got two blocks and I put one lying down flat and the other sitting up upright, would I get the same or a different surface friction? Well, if we think about those microscopic bumps a bit, this block here, it's got a larger surface area exposed. And that means that there's more bumps. But the bumps don't have as much pressure on them. They're not pushed into the grooves as much as they would be in this case here, because the weight is being distributed over a larger area. So even though you've got more bumps, you've got less pressure, less force per area, less weight per area, and as it turns out, those effects cancel each other out, and contact surface area does not have an effect. Your next guess would probably be the weight. And that's certainly true. If you've got a certain amount of friction because you've got a block on a surface, and then you put a weight on top of that block, of course the bumps get pushed down more deeply and you end up with larger friction. However, a better concept than the weight would be the normal force. The normal force and the weight are equal to each other if you're on a flat surface. Normal force and the weight are the same thing. But if you're on a incline here, then it's really the normal force that will be equal and opposite to the force pushing against the surface. So the bigger your normal force, the more those two surfaces push against each other. So normal force is going to be a very important factor affecting friction. And the last thing you're probably going to guess, or maybe the first thing you guessed, would be the nature of the surfaces themselves. So if you've got wood on wood, the bumps are going to be different, and that's going to cause a different amount of friction than if you have, say, wood on snow. And this is all going to be taken into account with something that we call the coefficient of friction. We'll use a mu s for the coefficient of static friction, and we'll use a mu k for the coefficient of kinetic friction. Now these coefficients of friction, they only depend on the nature of the surfaces involved. That means if we want to look up a coefficient of friction, all we have to bring to the table is what's the nature of the surfaces. Is it wood on wood? Ice on ice? Is it metal on metal? Etc. And then we can find out a coefficient of static friction and a coefficient of kinetic friction. And you'll notice that the values for the static friction are larger than, greater than, those for the kinetic friction. You'll also notice for pretty much every one of those entries, the coefficient is less than or equal to 1. The only common case where we have a coefficient of kinetic friction equal to 1 is when you've got rubber on something like cement. And in that case, the coefficient of static friction can actually be quite a bit larger than 1. But by and large, all the coefficients are less than 1. Okay, so let me recap. We said that the force of friction depends on two factors. One is the normal force, and the other depends on the nature of the surfaces, the coefficient of friction. And so you're probably asking yourself, well, what's the relationship between the force of friction, the normal force, and the coefficient of friction? Well, it's as simple as it could be. The force of friction is equal to the coefficient times the normal force. Or if we rearrange that, we'll get that the coefficient is equal to the force of friction divided by the normal force. And you'll recall that the coefficient of friction was almost always between 0 and 1. And so if you combine that with the fact that the coefficient is really without units, because we're talking about a force divided by a force, we're talking about newtons divided by newtons. So that really implies that mu is without units. It's unitless. So what mu really is it's a fraction of the normal force. And what I mean by that is, let's suppose we consider an object on a flat surface, which would mean that the normal force and the weight would be the same size. And if we pushed it at constant velocity, then of course the force of friction would have to equal the push force. So in order to lift the object, we've got to lift it with a force equal to the weight, or the normal force. And that normal force is always going to be bigger than the force of friction. That is the force you have to push it with. So it's always harder to lift an object than it is to push. And the coefficient of friction is just sort of saying, how much easier is it to push than to lift? When you're thinking about the coefficient, think fraction. Is simply what fraction is the force of friction of the normal force.
Now, if we want to calculate frictional forces, we have to distinguish between three distinct cases. The first case is when our object is not moving. So we can imagine this situation. It's not moving, therefore the forces must balance out. So if we push with a force P, then the frictional force is going to be equal to P. Those two have to be the same size. So we could have used a smaller push, and we'd have a smaller frictional force. Or we could use a bigger push, and if it still doesn't move, we'd have a bigger frictional force. In that case, we're really just considering the inequality here, so we don't really know the value. So when it's not moving, we can say that our force of friction must be equal to whatever we're pushing with, and it doesn't move. Now, when it initially begins to move, that's when you can use this equation with the equality. The force of friction in that case will equal this coefficient of static friction times the normal force. And then once it begins to move, when we've got continuous movement, we can calculate the force of friction as the coefficient of kinetic friction or dynamic friction times the normal force. The IB calls it the coefficient of dynamic friction rather than kinetic friction.
So how would we go about measuring a coefficient of kinetic friction? We know the coefficient of kinetic friction is given by the force of friction divided by the normal force. So we just need to find a force of friction and a normal force. We can use a very simple apparatus. We're just going to place a block on a flat surface. And then we're going to take one of those Newton scales and pull the block. And we're going to pull it at constant velocity. So constant velocity, translational equilibrium, that means that all of our forces have to be balanced. There's got to be no net force. So if I do a free body diagram of my block, there will be a normal force up that's going to have to cancel out with the weight. Those two have to be equal in size. That means if I know my weight, I know my normal force. And then if I consider in the horizontal direction, once again, the forces have to balance out. So if my Newton scale is reading a value P here, my force of friction has to be exactly the same size. So whatever my reading is on my Newton scale, that's going to be equivalent to the magnitude of the force of friction. And that means my mu k will be equal to the push force divided by the weight mg. So for instance, let's say my push force came out to be 3 newtons. That's what the Newton scale was reading when we pulled at constant speed. And let's suppose was 2 kilograms. Then my coefficient would be equal to 3 newtons divided by 2 times g, or approximately 20 newtons. And that would make my coefficient equal to 0.15. So now we ask the question, well, how could we measure the coefficient of static friction? Well, we could do it in a very similar manner to what we just did with the kinetic friction. We could just pull a block, but we'd measure the force at which it first begins to move. And that force should be a little bit larger than the force to pull it at constant velocity. But I want to show you another method of doing it using an incline. So we've got a block, or whatever our object is, on an incline. And what we're going to do is increase this angle theta. We're going to do it very, very slowly. And what we want to do is measure that angle when the block first begins to slide. Now to understand how this works, we need a free body diagram. So let's do a free body diagram. Of course, we'd have the weight straight down, mg. We'd have a normal force perpendicular to the incline, and we would have the force of friction. And then, as we always do with incline problems, let's break the weight up into components along and perpendicular to the ramp. So here's the component perpendicular to the ramp. Here's the component along the ramp. This angle up here would be theta. And of course, this component here that's opposite the angle is going to be mg sine theta. This component here perpendicular to the ramp is mg cos theta. So we're effectively taking this vector mg out of the picture and replacing it by these two components. So now what we can do is just consider the forces here perpendicular to the incline. Well, we know the block doesn't raise off the incline. We also know it doesn't dig into the incline. That means those two forces have to be balanced. And that means the normal force here has to be the same size as mg cos theta. Those two are going to have the same magnitude. Now, what's going to happen as you increase this angle very, very slowly is the force of friction will always match mg sine theta until you reach a point where it first begins to slide, and then the force of friction can't keep up. And as soon as mg sine theta is just slightly bigger than the force of friction, it's going to begin to slide. But because it can be just infinitesimally larger than the force of friction, we can say the two are equal. We can say that when it first begins to slide, this force of friction should be equal to mg sine theta. So we have another expression here. The magnitude of the force of friction must be equal to mg sine theta. So now when we go to calculate our coefficient of static friction, it's going to equal the force of friction divided by the normal force. But our force of friction is mg sine theta. And our normal force is just mg cos theta. mg's are going to cancel out, and you're left with this expression that the coefficient of static friction will equal the tan of the angle where it first begins to slide. So if we were talking about, say, a wooden block on a wooden surface, then we should get a coefficient of static friction of about 0.4. And that means the angle at which the block will first begin to slide should be about 22 degrees. That is, the tan of 22 degrees is approximately 0.4. Okay, here we have a word problem. What I'd like you to do is to pause the video, read the question over, try it for yourself, come back for the answer. For any problem, a good place to start is your free body diagram. So we've got some block, it's 5 kilograms. I'm going to make a little simplification and take G equal to 10 newtons per kilogram just to simplify the math a bit. Free body diagram, well, we've got this pulling force of 15 newtons. We've got a weight coming down, which will be 5 kilograms times 10 newtons per kilogram, or 50 newtons. That means my normal force has to be exactly the same size, which is 50 newtons. And then pulling to the back here, we've got the force of friction. So I need to figure out how big my force of friction is, and that simply has to equal the coefficient of friction times the normal force. Coefficient of friction, what you're going to have to do to get a coefficient of friction is to look it up in a table. So here's my table, and for wood on wood, I get a coefficient of kinetic friction of 0.2. So this is going to be 0.2, this is the kinetic friction, 0.2 times 50 newtons, which is simply 10 newtons. So now if I want to get the acceleration, that's going to be the net force divided by the mass. Net force 15 newtons minus the force of friction, or 15 newtons minus 10 newtons. The mass was 5 kilograms, so I end up with an acceleration of 1 meter per second squared. Here's a second problem. Pause the video, read the question over, try it out for yourself, come back for the answer. Okay, so in part A here, we would like to get the coefficient of static friction, which has to equal the force of friction divided by the normal force. Now we're on a flat surface, that means the normal force has to be equal in magnitude to the weight mg. And the other thing that we know is that the push force, that 350 newtons required to just get it going, would occur when the push force is exactly equal to the friction. And that means the force of friction has to equal that push force. So we're going to get 350 newtons divided by, and once again I'm going to make this simplification just to make the math a little easier, but I'm still assuming 2 significant digits, even though it really isn't. G is equal to 10 newtons per kilogram. And that will mean that the weight is going to be equal to this 200 kilograms times 10, or 2,000 newtons. Notice the newtons cancel out, so we get an answer there of 0.18 for the coefficient of static friction. Now in part B, I'm going to start with F net equals mass times acceleration. And I'm trying to push a mass of 200 kilograms. And I'm told some information that gives me the acceleration. It changes its velocity by 2.0 in a time of 5 seconds. So this is the acceleration. Net force, well, that's going to be the push force minus the force of friction. And we're going to assume the same push force as in part A, which was that 350 newtons of push force. The force of friction will equal the coefficient of kinetic friction times the normal force. We're on a flat surface, so that's just going to be the weight mg. And then if we multiply this out, we get 80 newtons on this side. So now I've got that 350 minus mu k, that's what I want to find out. The weight here was that 2,000 newtons, and that's supposed to equal to 80 newtons. I'll let you do the math there. You should get a coefficient of kinetic friction equal to 0.14 in part B.
Okay, let's summarize the big ideas from the video. A very important idea was that the force of friction depended on 2 factors. There was how much force was being pushed so that the grooves would sink into each other. And that is really the normal force. And the other thing that the force of friction depended on was the nature of the surfaces. So this normal force, if you're on a flat surface, it's generally equal to the weight. mg. If you're on an incline, it would be mg cos theta. The nature of the surfaces, that's taken into account with these coefficients of friction. And we had a coefficient of static friction and a coefficient of dynamic friction. And generally, these coefficients were just the ratio of the force of friction to the normal force. So they were just generally fractions between 0 and 1. And then when we got into the process of actually calculating these forces of friction, we had to distinguish between three unique situations. One would be if the object is not moving, in which case the force of friction will just equal whatever force you're pushing the object with, because those two forces must balance out because it's not moving. If it just begins to move, then you can use that the force of friction is equal to the coefficient of static friction times the normal force. And in the third case, that's when it is moving continuously, that would mean the force of friction would equal the coefficient of dynamic friction times the normal force. So please take the time to become a subscriber, sign up for notifications, become a member, become a Patreon, make some comments, ask some questions. Any of your participation is greatly appreciated. Thank you.
And that's all for today, folks. Thank you very much.